goal of Rosetta is the global characterization of Comet Churyumov-Gerasimenko. To do this, before we take too many measurements, we need to know the context of these measurements as they appear on the comet. For this reason, we have ROLIS, a downward-facing camera on the base of the lander, which takes effectively a series of aerial photographs throughout the descent, so we know what the landing site looks like and its context in terms of the general comet. Once we're on the surface, we have a series of cameras named Shiva located around the upper surface of the lander. You can see the 5 cameras there, and also a pair of Shiva cameras on the rear face just here, which can let us have a stereo pair image, so we can take 3D images of the comet surface in front of us. This lets us gauge the distance to objects in the field of view. Other spacecraft have imaged comets before, of course. Rosetta is different. The lander will get down and get dirty. It will get its hands dirty. It will interact with the surface of the comet. To do this, we have the drill just here, which can penetrate up to 20 centimeters into the surface and return samples. These samples can be imaged by a microscope in both visual and infrared light. This is another part of the Shiva instrument. After imaging, the materials can be burnt, can be combusted or pyrolyzed. The vapours from this can be passed into a pair of mass spectrometers for analysis. The first of these mass spectrometers is COSAC, which is geared more towards looking at the high-mass compounds, the long-chain organics, the hydrocarbons, the things which could possibly conceivably form life sometime in the future. As well as COSAC, there is Ptolemy, which is geared more towards the light compounds, the volatiles, the ices. So we're looking at water ice, we're looking at carbon dioxide ice. As well as the drill, we can interact with APXS. This is an alpha particle and X-ray spectrometer. With this instrument, we will bombard the surface of the nucleus with alpha particles and X-rays. We then look at the backscattered radiation to analyse the chemical composition of the surface. We can also take the temperature of the surface using this instrument just here, which is the lupus penetrometer. This penetrates into the surface, hammers itself in, is then released, allowing the lander to continue moving. Whilst this instrument takes a profile through the surface of the temperature and the thermal properties, there's a thermal imager located on the upper surface of the lander just here, which takes a context image. It measures the infrared thermal temperature of the area in front of the lander. Comets are active bodies. They're surrounded by plasma, and this plasma can carry a magnetic field. So we have ROMAP located just here. We can also measure the interior of the comet, by this I mean the deep interior, using an interaction between the lander and the orbiter. We have 2 antennae located here and here on the lander. These can communicate in a ping-pong fashion with the orbiter. Looking at differences in the signal as they pass from the lander through the comet to the orbiter on the far side lets us measure the internal structure to look for voids, to look for strata, to get an idea of what the comet's like on the inside, deep in the interior. Other interactions that take place are with the Casset experiment on the feet, which is part of the Sesame experiment. This instrument works in 2 main ways. It can communicate between the feet, so one feet will transmit a signal to be detected by the other feet. This lets us calculate and to understand the structure between the feet of the very near surface. Sesame can also look at, with Casset, the deep interior of the comet by listening passively to comet quakes, listening for activity within the comet, say gas being produced. As well as Casset, Sesame also includes the dust impact monitor located on the upper surface of the lander just here. As the name suggests, this monitors dust impacts. It's listening and feeling for dust particles being ejected from the comet nucleus and then falling back in to impact the sensor to be detected.
To perform all these science activities, the lander has to carry a few other systems as well, such as a central computer. The computer will coordinate in between the units. Then, in addition, there is a data storage. So all experiments which have been carried out store first the data in the data storage, and then the data get transferred from the lander with this small antenna system, which you can see over here, to the orbiter. We're starting our mission at a distance to the Sun of 415 million kilometers. Means we need a good power system which is divided into solar cells and batteries. The primary battery system is supporting the first science sequence and allowed each unit at least to get executed once. The secondary battery is then for the further mission and get charged via the solar cells. On the comet surface, the balcony sees a temperature of minus 160 degrees. This is not suitable to switch on any electronic inside the lander itself. Therefore, there is a power system and a thermal system which uses heaters to heat up the electronic units, but this is not sufficient. In the beginning, we do need something on top of that, which are these two absorbers. The absorbers are special coated plates which are catching all the sun, so the heat inside the lander, to the electronic unit, and this is sufficient to switch them on. What you see over here, this is the so-called cold structure, and all electronic is sitting on a so-called warm structure, which is totally isolated from the cold structure. In between there are two thermal tents, which supporting as well the thermal environment inside the lander.
All of this information together will tell us the life history of the comet. It will let us characterise the entire nucleus, surface, subsurface and coma. With this information, we can answer lots of questions around the origins of the solar system, the origins of, say, water in the Earth's oceans, and possibly the origins of life on Earth. There's a lot of information to be got from this small spacecraft.